Hi everyone, I am Thibaud Vendrely. I'm an intern at Quandela working in the theory team, and I work with Awad on the subject of certifying these devices. So in this video, I'm going to present you the subject of my internship, which is Tensor Network Simulation for Imperfect Boson Sampling. So if you haven't watched Awad's videos, Awad's video on boson sampling, I suggest you to watch it first because he explains well the basis of it. But to sum it up, the idea of boson sampling is to pass a single photon through a linear optical circuit, which is represented by a R-random unitary matrix, and then to detect the output and to compute the probability of having a given output. The thing is that boson sampling is hard to simulate on a classical computer because we need to compute the permanent of big matrix U, and if the number of mode is much greater than the number of photons squared, then this sum matrix has no other structure to exploit, and its permanent is hard to compute. So that is the case for perfect boson sampling, but actually real boson sampling is different because real boson sampling, the one that we have in the lab, is noisy and can sometimes be efficiently simulable. There are different sources of noise, which are loss of photons, distinguishability, which is when photons are not quite the same and so they don't interfere perfectly, and also multiphotons emission. And you can watch Marceau's video on that. He explains in more detail this part. Our goal is to see if we can build a simulator which is efficient for noisy boson sampling in order to test it against experimental boson sampling to see if experimental boson sampling can do better than the classical simulation of it. In order to do that, we use Tensor Network Simulation. Tensor Network are a set of algorithms which aims to approximate representation of quantum states. The problem with quantum states is that they are really hard to store in the storage of a computer because they need a lot of data. So for instance, if we have n modes and n photons, the number of accessible states is given by this formula. And so for 20 photons and 50 modes, it represents 10 to the power of 18 states. So in order to store this state, we need to approximate it. And that's what we do using a tensor network. So here is the formula for a general quantum state, with I being the number of photons in one mode. The state is fully represented by this coefficient C here. And we can see this set of coefficients as a big m-order tensor. And so using this tensor, we can define a set of operations on it, which would be like merging and reshaping indices or different kind of factorization. And using this operation, we can find a set of smaller tensors, which will represent in an approximated way our initial tensor. So there are a lot of tensor network algorithms possible. And the one that I focus on is called matrix product state. So the general idea of a matrix product state is to write our quantum state in a new basis, which is this formula here. So this formula is quite easy, but the important part in this one is the chi here, which is called the bond dimension, and which accounts for the number of values that we have in the sum. And so these bond dimensions can be fixed by us, and so we can choose the number of elements we take in the sum in order to do a simulation until it will link directly to the accuracy of the simulation. So another way of seeing this equation is to write it like that, where the C here are a product of those matrices here, gamma and lambda. And so the bond dimension chi is the size of the matrices gamma and lambda. The greater the bond dimension, the more accurate the simulation. So I will present you now how to use MPS simulation for boson sampling. So here is a linear optical circuit of 4 modes. And so if we want to compute the output for this given input state here, what we do is that we first initialize our MPS, so all the matrices gamma and lambda. And then we pass through each component of the circuit. And at each component of the circuit, we update the matrices. Once we are done, we have our MPS, which is fully updated. And so we can compute all the probabilities of the output that we want. This is what I've done in the simple case of 3 photons and 6 modes, which gives me 56 output states in the end. So above you can see an ideal simulation of this boson sampling, which would be one which is done with a bond dimension of 4086. And this one has been done using a source algorithm in Perceval and not MPS. And below it, you can see the results of the MPS with a different bond dimension. So I've done it at the left with a bond dimension of 4. And so you can see visually that the probabilities doesn't match the one of the ideal, so it doesn't work. For a bond dimension of 6, it gets better, but it's not quite the same still. And for a bond dimension of 8, we can see that there is no visual difference between the two graphs. We can choose the bond dimension of 8 to say that it is a viable minimum bond dimension for us. So for 3 photons and 6 modes, 8 seems to be a suitable bond dimension, but the problem is that boson sampling is still hard to compute and MPS method isn't magical. So this minimum bond dimension will still evolve exponentially in regard to n and m. But this is the case for perfect boson sampling and not necessarily for noisy one. And that's what has been proven with loss, because loss decreases the entanglement and MPO works better for low entangled states. So MPO is quite the same as MPS, but for mixed states. So for this presentation, you just have to think that MPO is the same as MPS. In the end, the minimum bond dimension evolves slower for a lossy simulation, which is something that we can take into account in order to make a good simulation of noisy boson sampling. So our goal is to make an MPO simulation using loss and also using multi-photons emissions, because we think that it will lower the entanglement also, and using distinguishability in order to make a state-of-the-art simulator of real boson sampling. Like this, we can use it to certify that experimental boson sampling has a sufficient level of noise in order to make better than our simulated one. Thanks a lot for watching this video. So this video was quite quick on Tensor Network, and there are a lot more to learn about them. So if you want to have more detail, you can contact me and I can explain you or send you more information.